have automated instrumentation that kind of flow the sample while it's flowing. You shoot actually on that, right? And so you use the detector to record what comes out, and from that you try to figure out what's the structure of the solution. So what you hope to see is, so you can trigger some kind of a structure change, either by, say, mixing that with some kind of chemical that you expect to interact with that, or maybe just, say, by doing something, say, even study the impact with light or something like that. Right? So you hope to see a structure change, and that's reflected in the data.
Right.
So that's one thing we do. Oh, and so for that kind of information, right, if you combine with what you get from photography from the LDY, or from maybe cryo-EM, right? So because those techniques give you a very high resolution structure. But in those techniques, what you see is sort of like a frozen structure. Right? Here you're studying the structure in solution, right? So they're still kind of free to kind of move around. And so that's how they're supposed to be sort of in real life, right? So in a way, it's a more sort of like a realistic experiment, right? But the downside, of course, is, so you're looking at these things, and so when you study these things in solution, the information you get is very low resolution, right? So in a way, it's like it's a, take off your glasses or something like that, right? So you can see the change, but it's very fuzzy, right? So it's most useful when you sort of have something that's if you sort of know, right? So I can see the outline right now,
right?
But I know already from other technique what the internal structure is, right? Then if you put the two things together, you might figure out something more. Say,
right.
So when you're syntacting, how would the internal structure change in order to give you that like a fuzzy change that you see using this technique?
Right.
So that's one. Another thing we do here, which is I'm actually setting up to do right now, is to look at biological tissues. So right now we actually look at a lot of plant tissues because they're relevant to the production of bioenergy. So basically, what we do is you take a bean, small bean, right? So if you have a sample, this is actually very much like a lot of the imaging experiments that's done on other beam lines, right? So you take a small probe, you kind of scan across the sample, right? So every step, you basically do a small experiment. And so by looking at how you're seeing things differently on the detector at each point, you put that information back together, now you get a map of what you're scanning. Okay? So in a way, now you're sort of like doing imaging of the sample, except that the contrast mechanism in this imaging method, depends on what you detect. Right? So we look at the scattering pattern, which corresponds to the sort of like the underlying structures inside the sample. Right? So for example, right, plant samples. Plants all have cellulose. Right? So when you're scanning, and if you use the information that corresponds to the cellulose structure to assemble that structural map, then you're really sort of like looking at, sort of say, the distribution